Okay, so welcome everyone to Guided Study Group Week 7 of Math 141. So I apologize for the late start if you guys are joining me online, but yeah, there was some internet connections problem over here, so it sounds a little bit like loud and a little bit noisy, and there might be some distractions in my recordings, so please forgive me for this time. There was some of the internet problem in Vietnam right now. So we're just gonna go ahead and get started with our regular review of the materials. So this week we're gonna be working over section 3.4 and 3.5. So basically the two last sections of materials for midterm 2, which gonna focus basically on maybe like horizontal and vertical and maybe slant asymptotes, and also how to actually put everything together using what we've learned so far since the end of midterm 1 until now. Things about like graphing, first derivative, maximum, minimum, local maximum, local minimum, extreme values, also concavity and inflection points that we learned last week. And then this week it's just gonna be asymptotes, like the train of how our functions looks like on the graph when x approaching infinity, or if there's any discontinuities in the graph. So section 3.4, give me a second, I need to pull it up. Okay, cool. So first thing about 3.4 is that we're gonna learn about horizontal and vertical asymptotes. So to find horizontal asymptote is the horizontal asymptotes is defined as line y equal L if you have limit of x approaching infinity or negative infinity of fx equal to L. Now be careful. One of the things to pay attention to is that when you have limit of x approaching plus or minus infinity of square root of x squared plus something over x, now you have to know how to take this x out of the square root. So say for example you have x approaching infinity of square root of x squared plus something over x, then I think in one of the previous sessions I already mentioned that this one, when we take x out of the square root, is going to be x square root of the number, which is 1 plus something else, whatever in here, divided by x squared. So whatever in the dot over here is going to be that divided by x squared. And you have x here. So it will essentially cancel out, and that's going to be limit of x approaching infinity, square root of 1 plus dot over x squared. This thing is over x squared. And divided by 1. However, if you have limit of x approaching negative infinity, then the limit of x approaching negative infinity of square root of x squared over x, this one is going to be limit of x approaching negative infinity, negative x, 1 plus something divided by x squared, and then this one is x. So this x and this x cancel out. So we have this extra minus in the front. So that's what you have to be careful about when you find the horizontal asymptote, by taking the limit of x approaching infinity of x approaching negative infinity. We also have a theorem saying if you have r is bigger than 0, it's a rational number, then limit of x approaching infinity of 1 over x to the r is 0. And if r is a rational number such that x to the r is defined for all x, then limit of x approaching negative infinity of 1 over xr, x to the r is equal to 0. Now, this one allows us to find things like if you have limit of x approaching infinity of say 1 over square root of x, this one's also 0. Then you have limit of x approaching infinity of 1 x maybe to the 2/3 is also 0. However, if you have limit of x approaching negative infinity, there's a thing is that you cannot have something like 1 over square root of x, because now you have 1 over square root of a negative number, so that wouldn't work. But something like cubic root of x is going to work, and it's going to equal to 0. And similarly, if you have limit of x approaching negative infinity of maybe 1 over cubic root of x, and then you have its square, then you have this one is also 0, because fifth root of x is x doesn't have to be positive to take the fifth root, and then when you square that number, it's basically just a negative number square. So 1 over something very positive and very big. So it's going to be 1 over, it's going to equal to 0. Then we also have, so we're going to get started with the first example of today, which is question A of section 3.4 in the book. So it's asking us to evaluate the limit and justify each step when you have limit of x approaching infinity of the square root of 9x cubed plus 8x minus 4 divided by 3 minus 5x plus x cubed. So we have limit of x approaching infinity, cube square root of 9x cubed plus 8x minus 4, and then you have 3 minus 5x plus x cubed. So clearly here for both of the terms in the numerator and denominator, you can see like the dominant terms is x cubed because x is approaching infinity. So x cubed is going to be bigger than any value of x and bigger than like just a constant like 4 or 3. Therefore, that is the term that really actually matters. So when you take this limit, you take x cubed out and x cubed because both of them are positive. So you have 9 plus a over x squared minus 4 over x cubed. Actually here it doesn't really matter if it's x cubed or is it x squared, because as long as you have things cancel out here, then your problems will be so much easier to solve. Then you have 3 over x cubed minus 5 over x squared plus 1. Now you can see here that's x approaching infinity. Here you have x cubed and x cubed. Their numbers are different from 0. So you can cancel them out, and eventually you have limit of x approaching infinity, square root of 9 plus ax over a over x squared minus 4 over x cubed divided by 3 over x cubed minus 5 over x squared plus 1. And then this one is now just gonna equal, this is 0, 0, 0, 0 as x approaching infinity. You have square root of 9 over 1, which is going to be 3. That's my final answer here. And so the thing that you really need to care about is that you make sure that you can see what is the dominant terms in the numerator and denominator. Now we're going to go to the second example. Find the vertical asymptotes of fx equal x cubed minus x divided by x squared minus 6x plus 5. Now the vertical asymptotes is finding by, I kind of forgot to mention it in the review notes, but the vertical asymptotes is finding by first you factor out the denominator, and it usually happens for fractions because vertical asymptotes is like one of the points that you are not defined in, say, your function. And that usually happens when you have a fraction as your function, because then you have the denominator and your fraction will not be defined and will not be continuous when the denominator is 0. So you factor this one out, it's going to be, and I also factor out the numerator just like for the purpose of taking the limit. And I think it's a very good practice for all of the problems because you can actually see where things cancel out in your problems. So now the vertical asymptotes is going to give us 1 and 5. Now let's take the limit at 1, x approaching 1, like on both the left and the right, and also x approaching 5 on the left and the right, and see if it's give us any number. Or if it's give us a number, then it's not like, you know, discontinuous. It might not be discontinuous there. But if it's giving us like plus or minus infinity or does not exist, it means the fact that you're going to have a discontinuity there. So what we're going to find is that we'll have limit of x approaching 1 plus of fx, which is going to give us limit of x approaching 1 plus x minus 1, x plus 1, divided by x minus 1, x minus 5. Now we have x approaching 1 plus, then x minus 1 is approaching 0 plus, but it's not 0. So we can cancel these out, and what we have is limit of x approaching 1 plus x plus 1 divided by x minus 5. Therefore, we have this one is going to be 1 multiplied 2 divided by negative 4, which is going to give me negative 1/2. Now we have limit of x approaching 1 minus fx. Now note the fact that if we take the limits and it's giving us the same number and it's equal to, then you can say like, you know, your fx is your fx has like a jumped or removable discontinuity there. You have x minus 1, x plus 1. Then it's going to give us, give me a second actually. X minus 1, x minus 5. Now it's going to give us limit of x approaching 1 minus. Sorry, it's 1 minus. We have x plus 1 again, because x minus 1 is only approaching 0 minus, but it's not 0. So we can still cancel it out and still we get negative 1/2. Therefore, we have fx has discontinuity at x equal 1, but it's not a vertical asymptote. Now we find limit of x approaching 5 plus and 5 minus, the same thing. We're gonna have limit of x approaching 5 plus. Then we have x minus 1, x plus 1, x minus 1, x minus 5, and x approaching 5 plus. So these two cancel out because it's just a constant. Then we have, it's going to be 5 multiply 6 divided by 0 plus, which is going to give us positive infinity. And now if you do the same thing, x approaching 5 minus of fx, it's going to give us negative infinity. So therefore, we concluded that our vertical asymptote is where you have x equal to 5. If you draw it on the graph, it's going to give us something like this. So if this is 5, then on the right of 5 is going to approaching positive infinity, and then on the negative 5 is going to approach negative infinity. And so in this case, this is going to be a dashed line because there's no value at 5. Now, we're going to continue with question 50 of section 3.4. Find the horizontal asymptotes and use them with concavity and interval of increase and decrease to sketch the curve y equal x over square root of x squared plus 1. Now, first we find the horizontal asymptote, and then I say we find that by finding the limit of x approaching infinity and negative infinity of the function. So let's get started. First of all, we look at this function, and I would highly recommend doing this is to identify the domain. So in case you find a discontinuity, but then it wouldn't mean anything if that point is already not in the domain, right? So your domain here, you can see that it's R because in the fraction, the denominator of the fraction has x squared plus 1, which is always a positive number. So when you take square root of that, the value is always going to be defined because it's always positive. It's only not defined when it's equal to 0, which is not right because x squared plus 1 is always positive. Then we find limit of x approaching infinity of fx, which is going to give us limit of x approaching infinity, x over square root of x squared plus 1. And as I say earlier in the review slides, as x approaching infinity, you can take the x out of the square root, and it's going to equal limit of x approaching infinity, x over x, and then you have 1 plus 1 over x squared. So this one coming from this x squared, if you divide x squared by both sides and multiply x squared outside, no, actually from here to here, basically one step I did is that you multiply x, and then x squared over x squared plus 1 over x squared. How can I actually do that? In this case, x is equal to square root of x squared. But when x approaching negative infinity, then you have x equal negative of square root of x squared. Now you can cancel out this x, and then what you have is limit x approaching infinity, 1 plus square root of 1 plus 1 over x squared, which is going to give us 1. Now we'll do the same thing of limit of x approaching negative infinity of fx. So one horizontal asymptote is y equal to 1. Now the second one, if you do the same thing, what you have is that you're gonna have is equal to -1, and the horizontal asymptote is going to be y equal to -1, which means when x approaching infinity, your y is going to approach 1, but when x approaching -infinity, going the other way, then y is going to approaching -1, and we're going to see that in the next question when they ask in the next part when they ask us to sketch the curve. We only need to find more about the concavity and interval of increase and decrease. So we have fx be x over square root of x squared plus 1. If you find f prime of x, and I'll do this one quickly because derivative is not really like a theme of discussion in this exercise. Then you have x multiply half of 2x over square root of x squared plus 1 divided by x squared plus 1 because it's the square root square. So what we have here is going to be square root x squared plus 1 to the 3 half divided by 2 and 2. Then you're going to have x squared plus 1 minus x squared, which is going to give us 1. And this one, as we said earlier, x squared plus 1 is always positive. So you want to take it to the power of 3 half. It's always a positive number. So 1 over a positive number is always bigger than 0. So it always increases. So the function only goes up and it doesn't fluctuate at all. Then we need concavity. So we need a second derivative, which is here we have x squared plus 1. So basically here the first derivative is x squared plus 1 to the 3 half, to the negative 3 half. Then here we take it's going to be negative 3 half, this one to the negative 5 half, multiply 2x, which is going to give us negative 3x divided by x squared plus 1 to the 5 half. Again, the denominator is always positive. So all we care about is now the numerator. So this one is going to be positive when x is negative, because here you have negative 3. So the entire fraction, the sign of the entire fraction is decided by the sign of x. So when x is negative, negative 3x is going to be positive. And over a positive number is going to be positive. So when x is negative, the entire thing is positive. So that one, x negative, is going to concave upward. And then it's going to be negative when x is bigger than 0, which is when it's concave downward. And it's going to equal 0 when x is equal to 0. That is the inflection point at 0, and then when you plug in 0 in, so you got 0, 0. So your inflection point is going to be at the center, at the origin. So the graph right now is going to look like this. So you have your inflection points here, and then you have the line. This one is y equal to 1, and this one is y equal to negative 1. Now, as x approaching infinity is approaching this line, and then it's approaching this line. And then from our discussion and analysis on the first derivative, it shows us the fact that the function is only increasing. So it only goes up. So it will only go this way. And it will not go like fluctuate in between. Because some people might question me like, why wouldn't it go this way? Why wouldn't it go the other way? Well, I mean, you don't know if it's gonna cross your value or not. But one thing I can look for sure here, one thing to look at this is that x, when x approaching infinity, like this way, x is always gonna be, oh yeah, a very clearly thing. If you go here, you don't know if it's going this way or this way, right? When you have x over square root of x squared plus 1, x is equal to square root of x squared when x is positive, right? And this one is smaller than square root of x squared plus 1. Therefore, the entire fraction is always smaller than 1, and it can only approach 1 as x approaching infinity. So therefore, it's always below this line. And the same reasoning can apply for this line, whether it's here or is it down here. And then you're gonna see that actually it's up below above the horizontal asymptotes because it's always gonna be bounded by -1, but it will never reach that values. So that's example 3. I'm gonna go ahead and go to 3.5. If you're following me online or like watch these videos again, please feel free to email me or like schedule a meeting with me, or like just send me a text on Canvas telling me, okay, I don't understand this part, and then I'll try to set up a time and explain it to you in person. So, because like no one actually is joining me online right now. So let's go to section 3.5. So 3.5 is where you actually put everything together, and we have a checklist for code sketching. So whenever they give you a functions, if these are the elements that you need to be able to derive so far from what we've learned since midterm 1 and everything in calculus so far. So we have the domain, intercept, either an x and y intercept. So these are pretty basic, and you don't even need to take 140 to know about these. And symmetry, so these you should already know in like geometry or maybe even like trigonometry in high school, or any math classes you have to take before calculus. Then we have asymptote, which we just learned in 3.4. So I expect like some of you might be struggling with this right now, trying to put it into like everything at once. Vertical asymptote, horizontal asymptote. The slant asymptote is the new thing in section 3.5, where you actually learn and to use how to use the long division to actually find the slant asymptote. And then you have interval increasing and decreasing, which we learn in 3.2 or 3.3 about the first derivative test. And we have local maximum and local minimum using the first derivative test. And also we from the finding of the critical values. And then we have concavity and inflection point, which comes from the second derivative test. And where the inflection point is, again, where you have your second derivative change signs. So how to find the slant asymptote? So the slant asymptote is defined as the line y equal mx of mx plus b. If you have limit of x approaching infinity, fx minus mx plus b, or mx minus y equal to 0 at x approaching infinity. Where you have m is different from 0. So it is actually a slide with a slope. So you have, when m equals 0, you have a horizontal asymptote. That's pretty clear. Typically, it's usually applied for rational function, which has the highest power in the numerator, highest degree in the numerator is 1 plus highest degree in the denominator. Because then, when you use the highest degree, say you have x cubed over something x squared, so the difference is 1x. So that's actually, see here, like you see the power of x is 1. So that is a line, and it shows us the fact that the line has some slope, and that's one of the sides I show you is a slant asymptote. Then you take y equal fx as the result of the long division of the numerator by the denominator. And that value of y is going to be mx plus b, and that's going to be your slant asymptote. We're going to see that in this first example 4. So find the slant asymptote of fx equal x cubed minus x divided by x squared minus 6x plus 5. Now, using long division, this is how you're going to do it. The way I think some of you might have learned it before in high school, trying to like divide it x cubed minus x by x squared minus 6x plus 5. Here you're gonna write it as x cubed minus x, and there's a space in between because you jump from x cubed to x. So there's the square power here, and this is the 0 power, which is a constant part. So I'm just writing it as plus 0x squared minus x plus 0. Now the first thing to use in long division is that you just care about the highest power. So you're gonna divide x cubed divided by x squared, which is gonna give us x. Now, after that, you multiply back to subtract and see what we have left to divide. So you have x multiplied by x squared is x cubed. But when you go over here, you're going to change the sign, negative x cubed. So And then you're gonna do the same thing. You have negative 6x squared. Go over here, it's gonna be plus 6x squared. Plus 5x. Go over here, it's gonna be negative 5x. So what we have left is 6x squared minus 6x. And the highest power here and the highest power here, use two divisible. 6x squared divided by x squared is going to be give us 6. We have plus 6, and then you're going to multiply back again, which is going to give us negative 6x squared, negative 36x, so you're going to be plus 36x plus 30, going to be negative 30. So it's going to give us 30x minus 30. So we have limit of x approaching infinity. So this is going to be your function of slant asymptote. You're going to have x approaching infinity, fx minus x plus 6. So you're going to have limit of x approaching infinity. Basically, from this long division, I rewrite the term x cubed minus x equal to x plus 6 multiply x squared minus 6x plus 5 plus 30x minus 30. So when I rewrite it this way, your value of fx is going to give us x cubed or minus x, which is going to be replaced by this term, x plus 6, x squared minus 6x plus 5 plus 30x minus 30. Divide the entire thing by x squared minus 6x plus 5. Now this one is going to give us limit of x approaching infinity. Now, if you break this fraction into two different fractions, so this term over the denominator and then this term over the denominator, you're going to be able to cancel out x squared minus 6x plus 5 on the left, which you're going to have, oh, I forgot this part. You also have a minus x plus 6 here, as I mentioned, minus x plus 6. So you break it down. If you break it down, you're going to have this x plus 6 minus this x plus 6. And what we have left is limit of x approaching infinity. 30x minus 30 divided by x squared minus 6x plus 5. And this one, clearly, as x approaching infinity, here you're going to have x and then x squared. The power in the denominator is going to infinity faster than the denominator. No, in the denominator is going to go to infinity faster than the numerator. So x is always going to be smaller than x squared as x approaching infinity. Therefore, you're going to have is equal to 0. Which means our conclusion is that y equals x plus 6 is the slant asymptote of fx. So I think here the most confusing part might be how you do this long division and how you actually put it to analysis here. So you must understand the fact that you do this limit of x approaching infinity, fx minus whatever result that you find here is going to give us a fraction that's going to lead us to 0 as x approaching infinity. And so you're going to conclude that whatever you minus here as the slant asymptote. And one thing to notice, because it's called a slant asymptote and it's aligned, it should have the function of y equal mx plus b instead of maybe things like mx squared plus bx plus c. Then that one is going to be not a slant asymptote anymore, but it's going to be like, you know, some maybe like quadratic function that your function is approaching, but it's not aligned. Again, email me if you have any questions understanding this. If not, I'm gonna go to example 5, which is example 10 in your lecture notes. Sketch the graph of a function that satisfies all of the following conditions. Indicate a significant point on the graph. Now, they give us a bunch of conditions. And so we're gonna try to maybe like interpret some of these into from mathematical symbols into some geometric meaning so that we know how to graph it up there. And so I'm gonna give maybe like take a break for like a minute right here because I need to plug in the computers. But then you guys can work on it if you guys are listening to it online. Yeah, I think it's similar to what is already in your lecture notes, so you should already like start working on this. But if not, don't freak out. We're gonna be able, or if you already tried and you cannot get it and you don't know, or you don't know what you're doing is right or not, don't worry. We're gonna go through it in a moment. I just need to plug this thing in real quick. Where is this thing? Really far away from the power outlet. Yeah. Okay, so we're gonna go ahead and start interpreting the mathematical symbols that we get here. It's actually a sketch graph of a function that satisfies all the following conditions. So f(x) is continuous on negative infinity to -1 and -1 to infinity. So you have a discontinuity at x equal -1. Um, and then you have f of 0 equal to 0. So it goes through the origin. Limit of x approaching infinity of fx equal to 3. So one horizontal asymptote is y equal to 3 and y equal to -3. And it's on the two sides as x approaching infinity and x approaching -infinity. And then you have limit of x approaching -1 of fx is -infinity. So a vertical asymptote is when you have x equal -1. So, and it's approaching -infinity on both sides of -1. Then you have f prime of -2 and f prime of 3 equal to 0. And so you can conclude that it's one of the critical number. Is x equal -2 and x equal 3. Now, you're going to use the table of the first derivative test to find this. So you have x, then you have f prime of x, and you have fx. So what happened is you have -2 and 3, right? And then you have -infinity, -1, and then you have infinity. So you have f prime of x is equal to 0 here, and it's not defined here. So in this case, we have f prime of x is positive on -infinity to -2, so positive, and -1 to 3, positive. And you have negative on the other two intervals. Note that the double line here shows the fact that you have a discontinuity there. Therefore, you have a function increase and then decrease, increase, decrease. So you have both of these are maximum. Both of these. Now we look at the second derivative, and you have this -4 and 5. So you expect that you might have two inflection points, but you don't know. So you're gonna start graphing on what exactly is your value. So you have -4 and 5, and you have -1 in between, which is another continuous discontinuity. So then you have f prime, f double prime change sign from this is positive, and then this is negative, negative. Therefore, you have this one is concave upward, this is concavely, concave downward, and then concave upward. So from that, we have, let's start graphing it. So I'm gonna flipping back and forth the graph a few times. So first you have a discontinuity of x equal to -1. It's actually the vertical asymptote. So I'm gonna change the color to actually mark up what we already used. So we have here x equal to -1, which is here. Now this is -1. And then x is approaching -infinity on both sides. Oh no, y is approaching at -infinity on both sides of -1. Like this. And then we have goes through the origin. So it goes through the origin, so this might be here. That's included. And then horizontal asymptote at 3 and -3. So you have 3 as x approaching infinity, y equal to 3. And then you have y equal to -3. Then you have two maximum as -2 and 3. So this is the maximum here. Some maximum here, some maximum at -3. This is some maximum here as well. And then you have concave upward and concave downward. Therefore, you have from here it only increased from something here to going up. So it can't be above or below this one of -3, and we don't know. So but it only increased until -2. So -2, I think I made a mistake somewhere. It's it's -2 and 3, not -3 and 2. No wonder. -2 and 3. Here this planet, right? So like something here. This is 3, this is -2. It only increases and then it goes down. So it only goes down from here. So it's like that. Not crossing the line. And it's only increase here. So you can have it above or below. That's what the function didn't specify. So you can have it below this horizontal line, doesn't really matter. Then on the other side, it only increased from here to there as well. You have this one is going up, go through the origin, going down, and then it's only decrease. So it only approach like this. And now you have to write it as based on the concavity. So this is concave upward to concave downward. So it's concave upward until 4. So I'm gonna change here, maybe some points over here, and it's gonna approach like this, and then like this. And then it's concave downward from -4 to -1. So like that. So it's concave downward from -4 to -1, like that. Like it's a curve down. Then on the other side, you have its concave downward from -1 to 5. So concave downward from -1 to 5. So 5 is here. So you have to delete this because you wouldn't change your thing yet. Maybe somewhere here. And then you start concave upward. So you're gonna do upward here. So this is where you have the inflection points. So this is the other graph that I redraw after I finish the class. So just to make things clearer. So you have an inflection point here and inflection point there. You just don't know what their exact coordinates. It can be somewhere down here, but you have to make sure that it can only be concave downward, or concave upward the other way. So if you do it, it has to be like this way. So it cannot really be below it because then you're gonna have to go down and then go up. And then this part is gonna be downward, concave downward. This one is concave upward, and then this one is concave downward again, which is not gonna satisfy our proof for the concavity. And so this is like the part, the one that actually I think that it fits the best. It might have a mistake here that it didn't go through the origin. It should, but yeah, that is the graph that we should arrive at. And if you have any questions like not understanding some of the points, like why am I drawing this and how do I know that I'm going to draw that, feel free to email me and I'll get back to you as soon as possible. Finally, we have example 6. So it's like one of the things that we put everything together. So you have fx, you given fx, f prime x, and f double prime x, their formulas, and how. So you're gonna try to identify what is the graph of fx. So first of all, you're gonna see that the function is continuous everywhere, based on the denominator, like this, because it's always positive. So you're not gonna have any discontinuity at all anywhere. So this one's not right, this one's not right. And then this one's not right because it is continuous everywhere. Then you look at f prime of x, then you have the sign of f prime of x only depends on 1 minus x squared. And so you try to solve for 1 minus x squared equal to 0, and try to find, then you have x equal to -1 and x equal to 1. So those are the two special points that you should find some maximum or minimum. And if you actually think about it, you have x, f prime of x, and then you have fx. So it's continuous everywhere, so it's going to be -infinity to -1, 1, and then infinity. And there's no discontinuity anywhere. Then you have the sign of the entire fraction, as I say, only depend on the numerator, which is 1 minus x squared. And if you plug in some numbers, you're going to notice like this is positive, negative, and negative. So your entire function is going to be negative here, positive here, and negative here. And so it's going to decrease, and then increase, and then decrease. Which graph is going to give us that? It's going to be this one. Now, another thing to check back is to look at the concavity. So you can work out a concavity from here. Again, it only depends on the sign of x multiplied x squared minus 3. And so I'm going to do a little note here for example 6. So continue example 6. So it's going to give us x squared minus 3, and then you have f double prime of x. Now you have the place where you have 3 special point here. So you have negative square root of 3, 0, square root of 3, and then infinity. And then you have x squared minus 3 is equal to 0 here and here. And then f double prime of 3 is equal to 0 when x equal to 0 or x squared minus 3 equal to 0, which is going to give us at negative square root of 3 and square root of 3. Now you have x squared minus 3 is positive, negative, negative, positive. This one single stick doesn't tell you anything. It's just like it's telling if there's no discontinuity there. It's just saying it's a value. I don't really care what it is. And then you have f double prime of x. Here you have x is negative, negative, positive, positive. So now you look at, you have negative multiplied by a positive divided by a positive, which is x squared plus 1 something, as I say. It's going to be negative, positive, negative, positive when you have these two multiplied together. Therefore, you're going to have is concave downward from negative infinity to negative square root of 3, concave upward, concave downward, and then concave upward. So if you look back at the graph, this is concave downward here, like slightly slanted like this. Then it's go up, concave upward, concave downward again, and then concave upward. So this is a graph that satisfies the second derivative test, which I usually use just as a check back, because it's usually really hard to actually derive information from it, and it usually takes more time and with higher risk for algebra mistakes. So so that's everything I have for today. One final note before our exam review next week. Curve sketching and its characteristic is the main focus of exam 2. Try to do as many review problems in the book and review notes as possible. Next week, I'm just going to go through some of the problems in the practice exam, and I'm going to base that on your grades. So whoever did it, I'm just going to pick out the difficult question and solve it for you guys. So to help you guys kind of like direct through it if you don't understand the explanations or not. But if you haven't done the practice exam, I would say I'm just going to pick it by random, and it's going to be your loss because you wouldn't know what you missed out until you try the practice exam, and that's going to be a little bit too late for me to actually help you out. So with that in mind, I hope you guys have a great weekend and work on studying for Math 140, and I'll see you guys next week. Thanks a lot for joining me or rewatching the videos.